let's have a look at least the first couple of steps of this, namely drawing the diagram. So I've got a 10.1 due south vector, so that's about like this. 10.1 meters due south. Then my next vector is 18 meters long, 15 degrees east of north. Does that probably get further north than where I started? I would say so. That's my estimate anyway. All right, so I'm going to have to draw my reference line due north, okay, and then I'm going to go 15 degrees east of that. Okay, 18 meters. Here's 15 degrees east of north. This will be the y component. This will be the x component of that triangle. My resultant goes from start to finish. Okay, so it's going to look like that. Okay, so that's my overall displacement. This will be my vector. Okay, I'll have blue x and I'll have blue y. All right, everybody okay with that? Okay, that diagram is a bit overlappish. Okay, there's kind of no way around that though, with the directions I gave you. Yes, a lot of the stuff overlaps. Okay, next step is we got to calculate all the x's and all the y's. I'm going to assume that's probably where most people are at right now, is calculating all those numbers. All right, so for our black vector, the 10.1 meter long vector, x is 0. How do I know x is 0 for the 10.1 meters south? Right, it's due south. It's only going vertically. It doesn't have any horizontal east or west component to it, right? And that means then that y is 10.1 meters south. Right, so that's all I have to do with that vector. For the red vector, okay, red x is the opposite side from my angle. That means I'm going to solve for it using sine. So the sine of 15 degrees times the hypotenuse, which is 18 meters, okay, will give me my x component. My y component is the adjacent side, so I will use the cos of 15 degrees times 18 meters and get that. Okay, so we got 4.6587 meters, and that is east, okay, because I was finding this arrow here. And then my y component, okay, cos of 15 times 18, all right, 17.3867. meters, and that one is north because I just found this arrow here. Okay, that ringing a bell for everybody? I see some nods and I see some people with panicked stares. It's okay. I had fully intended to spend a couple of days on this knowing we'd forget some of it. Okay. All right. So now that I've got all the x's and all the y's, what I have to remember about vector component addition is if I add my x's together, I will get my resultant's x, which is blue. Okay, blue x. And if I add my resultant y's together, I'll get blue y. Everyone okay with that? All right, so adding the x's together is easy because I only had one vector that actually went east or west. Okay, and that's the 10.1 because this vector went straight south. All right, so the 10.1 meters east that I went during this part of the trip is the only x there is. So I don't even have to do any math with that one. It's 4.6587 meters east. All right, now north and south. I went 10.1 meters south, and then I did this 18 meters at 15 degrees. So I've got to take however far north I went, which is my y component, okay, and add it to that amount that I went south, or subtract the two, whichever makes more sense in your mind. Okay, so to get blue y, I'm going to take the 17.3867, and I'm going to subtract 10.1 meters from that, and that will give me my resultant's y. Okay, so this number right here, minus 10.1. Okay, gives me 7.2867. meters, and that is north, because I do end up going north after all this. So now I've got the two sides of my resultance triangle. Okay, looking at my numbers, my scale didn't work out exactly right, but it's still good enough. It was pointing the right direction at least. Okay, so now I can calculate what my overall displacement would be. That's D. Okay, because I now have blue X and blue Y, so I can use what? What can I use to get D? Pythagorean theorem. Okay, I have the two sides of that triangle. I can find the hypotenuse. So that's my first step. Find the magnitude of the displacement. So that'll be our 7.2867 squared plus our 4.6587 squared. And if we take those numbers, we'll get our resultant magnitude. So and I'm keeping all my decimals here, especially when squaring, because that can really mess with them. Okay, plus my answer squared. All right, gives me my resultant displacement is 8.6487. meters. Okay, so now I know how big it is. Now I need to find what direction it's going. Now, if you drew your triangle like this, that's fine. You're just going to get the complementary angle to what I get. Okay, my angle is going to be east of north. All right, so I'm going to use tan, and I'm going to use x over y. Okay, of course, at this point, we could use any trig function we wanted. Okay, theta equals tan to the minus 1 of my x component, which was the 4.6587, divided by the other side, which was 7.2867. All right, that'll give me my angle. All right, so I'm looking at a 32.59 degree angle. And that is going to be east of north. Okay, so now before I write down my final answer, what do I need to check? Significant digits. Okay, going back up here, 2, 2, 3. So my answer's got to have 2. All right, so that means that my final answer for the overall displacement is 8.6 meters at 33 degrees east of north, or I could also have 57 degrees, not 60, 57 degrees north of east if I drew the triangle the other way. Okay. All right, questions on that? Is it ringing a bell at least? Okay. It might take us a little while to get back in the groove of that, but that's okay. All right, so plan for this week, guys, is as follows. Obviously, you got your acceleration lab reports due on Wednesday, so make sure you're getting those finished. Okay. Today, we'll probably spend reviewing this. Tomorrow, we'll probably go into an activity just so that we're not spending like a bunch of days in a row doing this, because that'll get like boring really fast. Okay, so we'll do an activity tomorrow and probably the next day using some maps. Okay, we'll be doing some map stuff. Okay, it's vectors, but it's a little different than just doing add these vectors every time. Okay, so still working on kind of the basic skills that we'll do that tomorrow and Wednesday. Okay, Thursday probably come back to this, see how we're doing with it, especially since we'll have had 2 quizzes by then. I'll have a pretty good idea of where we sit. Okay, if we're looking pretty good, then Friday, Thursday, Friday, we might be doing the assignment on this stuff and then moving on. Okay, if we're moving on by the end of this week, okay, your unit exam will be less than 2 weeks away. All right, just so you're aware of kind of where we're headed here. Okay, but once we're good at this, there's just projectile motion to do, and that's the rest of the unit. So we'll be done easily. Okay, in less than 2 weeks. Okay. All right, questions on that one? Okay, so we left off, we were working on the worksheet there, okay? And I think this was the question I wanted you to do next, but we didn't get to it, okay? we were talking about boat questions. Okay, we talked about how when you're in a boat and you're crossing a river, okay, you have the rowing speed and the current speed, and they produce your resultant speed or resultant velocity, okay, and how to calculate that. This is similar, except it's a plane, okay? Planes are also boats. They're boats that go in the sky. Okay, so they work the same way. Wind blowing on a plane is the same as water pushing on a boat. Okay, it turns or pushes the boat, okay, or the plane in this case, in a different direction. This is something pilots have to account for when they are flying, especially when they are landing. Okay, if there is a crosswind, and they generally don't like to land in a crosswind, they have to trim it out. Okay, trimming it out means they have to push the rudder one way so that the plane actually flies into the wind and is pushed straight onto the runway. It works out very badly if they don't do that. Okay? Not landing on the runway is usually bad. Okay, so this is a kind of real world application kind of thing here. Okay, so I want you guys to give that one a try, keeping in mind that it works a lot like the boat questions that we did before the break, seeing how many of you remember the boat questions. All right, so give that one a try. I'll give you a few minutes and we'll go over it. Okay, so the boat questions and plane questions, they come in two kinds. They come in the kinds where you're trying to get across the river, okay, and they come in the kind where you're trying to get straight across the river. Well, I don't think we've done one where we were trying to get straight across the river yet, so that's the next one I'll put up. This one is one where we're just rowing across, but if you're rowing straight across, you don't end up going straight across, okay? And that's the case with this plane as well. It's not correcting for the wind, it's allowing the wind to push it in one direction, okay? So effectively, what we have here is the speed of the plane, okay, going north, 225 kilometers per hour, okay? And then we have the wind speed, which is 112 kilometers per hour east. Okay. They want us to find the resultant velocity of the plane. So effectively, what's the plane doing as a result of all of this? Okay, so that means we would need to find the magnitude and the direction of the plane. All right, so to find the magnitude, obviously it's pretty easy. They're already perpendicular, so I don't have to do any components. I already have the components. Okay, so that'll be 225 squared plus 112 squared. All right, so my resultant velocity there is 251.33 kilometers per hour. Okay, and then I've got to find the direction. Okay, theta will be tan to the minus 1 of the opposite side, 112, divided by the adjacent side, 225, okay, which should give me 26.5 degrees east of north. So I only have 3 significant figures here, so I would eliminate, okay, that, and I would have 251 kilometers per hour at 26.5 degrees east of north. Okay, everybody all right with that? All right, the other kind of boat question works a little bit differently. Okay, so we'll draw it as a river. Okay, but in this case, okay, the question would be worded this way. Okay, it says a person wants to row directly across the river or wants to end up straight across the river. Okay, it'll say wants to instead of is rowing. Okay, the other ones we've done said a person is rowing across the river. That means that's what they're doing, but they don't end up doing that. Okay, in this case, they want to end up straight across the river. That's the difference. You have to read the question carefully. Okay, so a person wants to row directly across a river. Okay, they can row a boat at, let's say, 2.1 meters per second. Okay, the river current is, let's say, 0.8 meters per second downstream. Okay, so I would say something like this. That's downstream. All right, so the question would say, what direction do they need to row? Okay. So obviously I don't point myself straight across the river in this situation. If I do that, I don't end up straight across the river. The current will push me downstream. I have to now row into the current at least slightly so that I end up straight across. So I already know what my resultant looks like. I know my resultant looks like this, straight across the river. That's what I want to end up doing. Okay, the two vectors that will add up to that are the river current, which is small, 0.8 meters per second downstream. Okay, now why did I draw it there? Yeah, well, I drew it because it's supposed to point downstream, but I also drew it because I want it to be part of the resultant. I want it and my rowing speed to connect the two ends of my resultant. Okay, I know my resultant has to point into the current, so I knew the current had to go on top. Okay, so my rowing speed is now going to go from here to there. And I know how big it is because they told me I can row at 2.1 meters per second. I'm not going to end up moving across the river at 2.1 because the current's going to do what? It's going to slow me down. Okay, I have part of my velocity in the same direction as the river current. So I go a little slower. That's why this time the resultant is not the hypotenuse. Every other time we've done this, the resultant has been the hypotenuse. Okay? In this case, it can't be because the resultant is actually slower because the current is going to take some of my speed away. All right, so what the question wanted to know was, what direction do I need to row? It just wants the angle. Okay? It doesn't even care how fast I'm going across the river. Another question might ask that, but in this case, it's only asking, what's your heading? Okay? What direction do you need to head in order to end up going straight across the river? All right, fairly simple for me to find that. Okay, I've got two sides of this triangle. I've got the side that is opposite my angle, and I have the hypotenuse. All right, what trig function is going to get me theta? Sine. All right, so I'm going to go sine to the -1 of my opposite side, 0.8, divided by my adjacent side, 2.1. Right, that will give me the heading I would have to go in. Okay. So okay, so that's telling me I would have to head into the current 22 degrees. And that would be my vector, 22 degrees into the current, because they didn't give me north or south or east or west in this question. They just gave me downstream. So I need to go 22 degrees upstream or 22 degrees into the current or something like that would be a good reference direction there. Okay. Now, there could be a part B on a question like that that's, again, asking you, how long will it take you to get across the river? Of course, in order to do that, they'd have to tell you how wide the river is. Because I hadn't planned on doing that, I didn't tell you how wide the river was. But okay, there could easily be a part B on that. And then you would have to find how fast you're going across the river. Okay, you'd have to find this side and then do V equals D over T, just like we had done before. All right. Okay, are those starting to ring a bell? Really, those are the only two kinds of vector addition questions you're going to run into in terms of boats. Okay, you could have going across or rowing across. Okay, going across, rowing across, and then obviously you have your vector component addition type of questions as well. All right, I'm going to give you about a 4 or 5 minute break here, and then we're going to get to work on some practice of this stuff. Okay. Number 7 here. So for number 7, okay, the vector we're given is that this thing is thrown at 25 meters per second, which is an impressive speed to throw it at, okay, at 40 degrees above the horizontal. All right, so this would be our initial horizontal component, and this would be our initial vertical component. We say initial because obviously the speed is going to change because this thing was thrown into the air, and what's going to affect it? Gravity is going to affect it. That's actually, this is how we start all projectile motion problems when we get to them, is we have to figure out how fast is this thing moving horizontally, how fast is it moving vertically, so we can calculate things like how long is it going to be in the air, how high is it going to go, how far is it going to go horizontally, because all of that is based on how gravity affects it and how fast and what angle you threw it at. Okay. All right, so we're going to find our initial horizontal, okay, or sorry, it wants the initial vertical first, so that's y. So y is the opposite side. So to get y, I would go sine of 40 degrees times the hypotenuse, which is 25, and when I do that, I should get 16.1 meters per second up, okay? And then to get the horizontal component, that's the adjacent side, so I would go cos of 40 times 25, and that should give me 19.2 meters per second. So that means it's moving at 19.2 meters per second horizontally. Okay, the 25 is at an angle, right? So it's moving 19.2 meters per second horizontally, and it's moving at 16.1 vertically. All right, everybody follow me on that? Okay. All right, let's keep going there with number 8 then. Okay, and 9. Let's see how we do on those. Okay, so for number 8, we got 3 different situations, okay? The river is always going south. So essentially, I would draw the river like this, okay? In the first situation, I've got the current going south at 1 meter per second, and then I've got the boat rowing south at 2.5 meters per second. It's collinear. If you row downstream, you go really fast, okay? Because the current pushes you, plus you have your rowing speed, okay? So obviously, our resultant there is 1 plus 2.5, because they're both south, okay? In B, the situation is opposite. I have the current going downstream, and then I have myself rowing backwards against it, or straight upstream against the current. Okay, so I have my 2.5 minus 1, leaving me with 1.5 meters per second north or upstream. Okay, and then the last situation, okay, is more like the ones we've looked at. Okay, so I have the current that is moving downstream, and I'm going west. Okay, so I'm rowing like this. Okay, at 2.5 meters per second. I have the stream going downstream like this at 1 meter per second, which means my resultant now looks like this. Okay, this would be my resultant velocity, and this would be the direction. It'll be south of west. Okay, and so all I do is do Pythagorean theorem here. So I have 2.5 squared plus 1 squared square rooted. That'll give me 2.7 meters per second for V. And then the angle is going to be the inverse tan of the opposite side, 1, divided by the adjacent side, 2.5, and that gives me my 22 degrees south of west, okay, for the direction the boat would head. Okay, everybody all right with that one? Okay, how many people have done number 9? All right, I'll wait a few more minutes before I do that one then. Okay, so with number 9, okay, we have a boat that on still water can travel at a speed of 3.0 meters per second. In other words, they're telling you the rowing speed of the boat, okay, 3.0 meters per second. It wants to travel north perpendicular to the river current. Okay, so here's our river. Okay, we're going to draw it like the rivers here that all flow which direction? East. Okay, in Alberta, all rivers flow east, because our border with BC is the Continental Divide, the highest point. It's where actually all rivers start flowing the other way. Okay, in BC, they all flow west. Interesting piece of trivia if you didn't know that before. Okay, so we have, okay, this river, that's not really an interesting piece, it's just fact actually. Okay, so the river current is 1.2 meters per second east. So there's my river current, 1.2 meters per second, it's going east. I want to end up going straight across the river. So here's my resultant. Okay, I don't know what it is, but that's what I want to end up doing. Okay, I know that I can row at 3 meters per second, but I'm going to have to row into the current in order to make that happen. So they want to know, in what direction do I need to head the boat? Okay, in what direction do I need to row in order to end up going straight across? So I don't even need to figure out what the speed is. I just need to figure out what the angle is. What direction do I need to row in? All right, so theta will be tan to the minus 1 of 1.2, my current, the opposite side, divided by, sorry, not tan, sine. Okay, inverse sine, sorry. Okay, of opposite over hypotenuse, 3.0. Okay, so when we do that, we should get 24 degrees west of north. Okay. Number 10 is very similar. How many people have done number 10? Okay, ready to go over that one then too? Okay, so on number 10, it says a boat travels directly north across a river. That means it's doing that. It's not being rowed that way, it's doing that. Okay, it's traveling that way. That's the same as wants to do this, ends up doing this. It's traveling directly north across a river. So again, I'm going to draw my river this way. Okay, I know that I end up going directly across the river. So whatever goes on, this is what I end up doing. And it does that at 1.0 meters per second. So they actually told me, here's how fast it's going to end up going straight across the river. The other piece of information I have is the river current. They tell me that that is 0.5 meters per second. Okay, and that's east. All right, so in what direction is the boat headed? All right, so this is what I would have to do in order to make that happen. I don't know how fast I'm rowing. And for this question, it doesn't matter how fast I'm rowing. It only matters direction. Which way am I rowing? So it's just like the last one we did. We're just looking for theta, except this time I don't have the hypotenuse. I have the other two sides. Okay, so theta this time will be 10 to the minus 1 of the opposite side, 0.5 over 1.0. Okay, and that will give me 27 degrees west of north. Okay, again, this is west, that's north. Okay, so we'll have 27 degrees west of north. Okay, everybody all right with that? So you do have to read the questions pretty carefully. If I was to give you one like this on a test, I would be abundantly clear that this is the resultant, or this is what you end up doing. I would like boldface, italicize, underline, put in capital letters, okay, all that kind of stuff so you didn't miss it, okay, so you'd have a better chance of doing it right, but you do have to read it carefully. Okay, so you can keep going on that, guys. Actually, you know what? Let's stop with the boat stuff. We've done enough of those now. Let's try, start on 13. Okay, try 13, 14, those ones. Those are the vector component addition questions, okay, like we've been working on, so let's give those ones a try there. Okay, so I assume most people are working on 13 here. I'm just going to draw the diagram just so you can double check that you've got it drawn correctly. Okay, so we have a boat that sails 150 kilometers at 20 degrees east of north. So north is my reference line. Okay, so there's a reference line that's going north. Okay, I'm going to go 20 degrees east of that, which is kind of a narrow triangle. So there's my 20 degrees. Okay, it's 150 kilometers. Here's my x component, it's going east. Here's my y component, it's going north. Okay. Then I draw the next vector on the head of the first. And my next vector is 265 kilometers, so a much longer line, 45 degrees south of east. So my reference direction is east. Okay. I need to go 45 degrees south of that. Okay, something like that. Might even need to be, yeah, that's about right. Okay, so here's my x component, here's my y component. X is going east, y is going south. This is 265 kilometers long. Okay, this is my 45 degree angle. So my resultant is going to go from beginning to end, and I'm going to draw the triangle kind of like this, which actually ended up to scale pretty good. Okay, this is theta. Okay, this will be my overall displacement. This x component is going east. This y component here is going south. All right, that's what my diagram should wind up looking like. Okay, you could draw the diagram. You could draw that triangle this way as well. Okay, there's nothing wrong with that. You're just going to get the opposite angle to me, or the complementary angle to me. All right, I'll give you a few more minutes on that. You can double check that you drew it right. And you got a bunch of X's and Y's to find. Okay, nice thing about this question, guys, is that second triangle has a 45-degree angle in it. What does that mean for your two sides? They're equal. Okay, I only have to calculate x. Y is the same as x because that 45-degree angle bisects the triangle. Okay, so you don't have to worry about those parts of it there. Okay, so just be on the lookout for that. Okay, that can save you a bit of time. So that's part of the calculations that have to get done. Find the x, find the y for both. Okay, then you're finding blue x. Both x components are east, so you can just add them. Okay. The two y components, however, are opposite. You have the black y that's going north. You have the green y that's going south. So you will have to subtract them when you find blue y. Okay. All right. We'll leave it at that. Okay. So let's have a look at what the calculations here are going to look like. So for my black triangle here, okay, my horizontal component, or the easterly part of the trip, is going to be the opposite side of my triangle. So for that, I'm going to use the sine of 20. Okay, which is my angle, times 150, which is my hypotenuse. Okay, then for y, it'll be, it's the adjacent side, so it'll be the cos of 20 times 150. For my green triangle, okay, I'm going to have that the horizontal component is the adjacent side, so cos of 45 times 265. Here's where you luck out. With a 45-degree angle, x and y are equal. You only have to do one calculation because 45-degree angle, okay, the two sides end up the same. All right, so you can save yourself a little time there. So here's what we are looking at on this one. Okay, we are going to have, first off, sine of 20 times 150. So we've got 51.303. And that's kilometers, and that's east. Okay, and then we got the cos of 20, not 220 times 150. All right, so that side's going to be 140.954. And that's kilometers, and that one's north. And then I've got to do the same thing for my green triangle. Okay, so x we already said is going to be the cos of 45 degrees. So cos of 45 times 265. All right, so that's 187.383 kilometers east. Since it's a 45-degree angle, the sine of 45 is the same number, so y will be 187.383 kilometers south. Okay, so I've got those all set up now. Right, so now I can move on to finding my resultants x. Okay, so blue x. Both x's are east, so I don't have to worry about subtracting or making one of them negative. They're both east. All right, so I'll take my 51.303 0215 and adding that to 187.383.297. All right, so my resultant x is 238.686 kilometers. Kilometers east. Okay, for my y component, okay, I'm going to have to subtract them because one goes north, the other goes south. So I'll take my 187.383 kilometers south and subtract the smaller north component, 140.954. Okay, I'll actually put in the real numbers so I get all the decimals here. Okay, so we'll have our 187.383.297 minus 140.953.8931. Okay, oh, 31, missed the one. Okay, so my resultant y is 46.429 kilometers. And that's south. Right? Now that I have those numbers, now I can figure out what my overall displacement is using Pythagorean theorem, same as before, and I can find theta using trigonometry. I'll probably use tan y over x, opposite over adjacent for me. Okay, if you drew the triangle the other way, then it's reversed. All right, so the overall displacement will be that 238 squared, okay, obviously with all the decimals in it, plus the 46 squared. And we'll put those numbers in, again, with all the decimal places. So 238.686 3185 squared plus our answer from the previous one squared. All right, so our overall displacement's magnitude's 243. We only have two significant figures though, so we'll leave that at 2.4 times 10 to the 2 kilometers, and then we'll get the angle. Okay, our angle will be tan to the minus 1 of my 46 divided by 238. Obviously with all the decimals in place. Okay, so second tan of 46.4294039 divided by, I lost it. Oh, there it is, 238.6863185. Whoa, I missed the decimal. All right, so we're getting 11, almost exactly 11 degrees, okay, and that direction is south of east. Okay, everybody all right with that? So those are a bit involved. They take a bit of time to calculate, but as we get more and more practiced at them, they'll go faster and faster. Okay. All right, I will post tomorrow's quiz shortly. Make sure you have a look at it. Make sure you're getting your acceleration lab report done. If there's questions, that's got to be tomorrow.